It is no secret to anyone that there is a very hot core at the center of the Earth. But did you know that it is slowly but inevitably cooling down? What will happen when this occurs? At a basic level, the Earth will become full. But if we look a bit closer, the planet's rotation will slow down, which will significantly alter the Earth's crust. This is just the beginning of the problem, as the convection currents in the mantle will disappear, meaning that the planetary dynamo will also vanish. The Earth will lose its magnetic field and become completely vulnerable to cosmic radiation, which will destroy all life on the surface. In addition to this bleak scenario, the solar wind will gradually blow away the Earth's atmosphere, transforming our planet into something resembling Mars. In general, the prospects are not bright, but our goal is not to scare you with the end of the world. Let's instead talk about the depths of our Earth, as few people know that it also has an external one. Few people know that it has an outer core and is in a liquid state. We know this because, after watching this video, it's quite likely that you'll become even more afraid of earthquakes. In general, it will be interesting as always. Meanwhile, we'll go into space to take a look at our home planet. Looking at this insanely beautiful little ball, we see that it's covered with water by about 70%. There are no mysteries here. Essentially, all the oceans just float over giant plates of rocks and mud that humanity once, for some reason, decided to call continents. In reality, it's a concept of buoyancy, in which objects with lower density rise above those with higher density, and the latter sink to the bottom. This can explain much more massive processes than the existence of oceans. Similarly, it can explain why solid water can float on liquid water, why do helium-filled balloons rise in the atmosphere, and why do rocks sink when we throw them into a pond. The latter only requires a different perspective. It's not the rocks that sink, but the water around them, which has a lower density and rises around the rock. This same principle of buoyancy explains the layered structure of our planet. Essentially, the atmosphere, with the lowest density of all the layers, floats on top of the liquid ocean, which in turn crawls along the solid crust of the Earth. The crust moves along the even denser mantle, which is ultimately unable to sink to the lowest and densest point, the core. Ideally, the most stable state that the Earth could be in would be layered like an onion, with the most dense elements toward the center, and each outer layer gradually made up of less dense elements. Each earthquake is a sign that the planet has taken another step closer to this ideal state, as after each earthquake, the speed and rotation, although small, increase. This is how not only our world, but also other planets are arranged. We just need to remember where all these elements came from. Long ago, in the universe, there was practically nothing but hydrogen and helium. Heavier elements were born thanks to the stars and returned to the universe after their death, forming the next generation of celestial bodies. However, this time a whole cocktail of new elements was formed: nitrogen, silicon, magnesium, carbon, oxygen, sulfur, iron. New stars and planetary disks begin to form from these elements, and almost every one of them has external pressure from the newly forming star, mainly pushing lighter elements to the outer parts of the future star system. At the same time, gravity causes instability in this disk in order to collapse and form what will soon become planets. Speaking of the solar system, the 4 planets with the highest density are located in its inner part today. They were unable to gravitationally retain large amounts of hydrogen and helium from which they were formed, so they didn't become gas giants. However, the outer planets, being more massive and farther away from the sun and thus receiving less radiation, were able to retain large amounts of these superlight elements and formed gas giants. Earth and other similar planets are structured in the same way. The densest elements are concentrated in the core, while lighter elements form less dense layers surrounding it. It's no surprise that the heaviest stable element, iron, which forms huge masses thanks to supernovae, became the most common element in the Earth's core. However, not everyone knows that there is a layer of liquid between the solid core and mantle at a depth of 2,000 kilometers, which is called the outer core. Our planet has a layer of liquid that makes up 30% of its total mass. We were informed about this by simply terrifying harbingers: seismic waves caused by earthquakes. There are 2 types of seismic waves that are caused. By earthquakes. The first is the primary wave, also known as the compressional wave. It is a kind of pulse-like tension on the surface. The second wave is the secondary wave, which is transverse in nature, and its path is similar to the movement of a wave on the surface of the sea. Both waves move outward from the origin points, transmitting the effects of their vibrations not only on the surface near their epicenter, but also throughout the world. This is why seismic monitoring stations analyze both types of waves. However, the waves do not pass through liquids, unlike the waves in Peppa Pig, which not only have the ability to break through liquids, but also refract within them. As a result, we know that the Earth has a liquid outer core, beyond which lies the solid mantle, and an inner core, which is solid. This is why the heaviest and densest elements are found in the core of the planet. But why is the outer core in a liquid state? All known elements, including iron, can take one of several forms depending not only on pressure but also on temperature. The stumbling block here was the fact that iron is much more complicated than most of the elements we know. It is capable of taking on various crystalline solid forms. However, speaking of normal pressure today is not at all interesting to us. We are heading to the Earth's core where the pressure is hundreds of times higher than in water and millions of times higher than atmospheric pressure. But first, it is important to understand that the density of the atmosphere is about 0.1/10,000th gigapascals, while in the inner core it is approximately 330 to 360 gigapascals. This requires simply astonishing temperatures comparable to the temperature on the surface of the sun, which, I remind you, is sufficient to melt iron. Nevertheless, at the same temperatures but at lower pressures, iron easily remains in a liquid form, and with increasing pressure it solidifies. What does this mean for the Earth's core? The highest temperature in the center of the Earth is just below 6,000 Kelvin, while the melting temperature of iron at the boundary between the inner and outer core is also estimated to be around this level. Our beloved Earth is gradually cooling down, releasing heat into space faster than it generates its own heat through radioactive decay inside the Earth. The internal temperature is decreasing, but the pressure remains constant. In other words, at the dawn of its birth, our native planet was even hotter than it is now, and it is possible that once the entire core was liquid. As it cools, the inner core continues to grow. The final stage is complete cooling and the formation of a giant piece of iron inside our planet. The density of solid iron and its enormous mass will cause the compression of our planet, resulting in just an enormous amount of earthquakes. Let's summarize. The liquid state of the core is due to its temperature, which allows iron to melt, albeit only where the pressure is lower. As the Earth ages and cools, more and more parts of the core solidify, leading to a slow and gradual compression of our beautiful planet. If you want to see what this will look like, just look at Mercury today. The same huge cliffs will appear on our planet. Mercury has long since cooled and compressed greatly, leading to giant cracks tens or even hundreds of kilometers long. We must remember that every earthquake is a warning sign that the Earth is getting a little closer to its final cooling and solidification. In ancient times, people were fascinated by the mysterious blue of the sky, which gave way to the darkness of night, filled with millions of shining stars. The depths of the oceans, which hide no less secrets than the land, have always been frightening. Even now, if you imagine the dark bottom, it can be a little scary. Millions of sparks, but the depths of the oceans hide no less secrets of humans. On the contrary, they always frightened. Even now, if you imagine the dark bottom, it becomes scary deep down inside. Isn't it true? Nevertheless, curiosity still takes the lead, and there are daredevils who cannot be scared, not by the depths themselves, but by what they hide. Despite the fact that more people have reached space than the ocean floor, some success has been achieved in this field. Even in the Mariana Trench, research vehicles have already descended. But sometimes it seems that, apart from the Challenger Deep, there are simply no other deep-sea places on our planet. However, we know that this is not true. There are many of them hidden in the oceans of the Earth, and today we will talk about one of them, the Kuril-Kamchatka Trench. The oceanic crust bends and sinks under the more massive continental crust, causing it to be compressed and partially pushed beneath the overlying plate. As a result, a trench is formed, reaching depths of at least 5 to 7 kilometers. The Mariana Trench, at more than 11 kilometers, is the deepest known trench in the world, while the Peruchili Trench, at almost 5 kilometers and 900 meters, is the longest. In fact, there are over 30 known trenches, all of which are under close scientific scrutiny, including seismologists. These locations on the ocean map often become epicenters of powerful earthquakes. Now let's travel to the Pacific Ocean, specifically to the area between the eastern slopes of the Kuril Islands and the southern part of Kamchatka. Here lies a narrow, underwater canyon known as the Kuril-Kamchatka Trench, which is more than 2,000 kilometers long and on average 59 kilometers wide. It was discovered by American scientists. Thousands of kilometers that we know as the Kuril-Kamchatka Trench were first discovered by the American vessel Tuscarora in the 19th century, and it carried this name for a long time until it was renamed by the Soviet authorities. If you look at the trench from above, you are unlikely to notice anything unusual. Despite being a huge fold on the ocean floor, it may not seem particularly special at first glance. However, this trough is part of a vast system of trenches along the western boundary of the Pacific Ocean, where lava flows from the depths and creates the Earth's crust. The maximum depth of the Kuril-Kamchatka Trench is believed to be 9,700 to 17 meters, although some sources state it may be up to 10.5 kilometers deep. In any case, it falls short of the acknowledged leader, the Challenger Deep in the Mariana Trench. The Kuril-Kamchatka Trench is part of the so-called Pacific Ring of Fire, a zone covering the entire Pacific Ocean, about 40,000 kilometers long. Many earthquakes and volcanic eruptions occur within this zone, which accounts for about 90% of all earthquakes on the planet and 81% of the most powerful earthquakes and volcanic eruptions. As many as 452 volcanoes are part of the Ring of Fire, and of the 25 largest eruptions in the past 11,500 years, only 3 occurred outside the Pacific Ring of Fire. The ring is formed by several zones of tectonic activity where one lithospheric plate sinks beneath another as the oceanic lithosphere grows, and where there is tectonic activity, there are various external manifestations of it, including volcanic eruptions and earthquakes. One of the participants in this eerie ring of fire is the Kuril-Kamchatka Trench, which is rich in all kinds of anomalies, such as the lifting of the mantle in the area around the island. The depth and seismic probing reveal a mantle uplift in the area around the Samashir Island. A significant aesthetic anomaly has been identified, indicating that the Earth's crust in this region experiences a deficit of power. However, anomalies do not end there. In the area belonging to the Central Kurils, there is a Vityaz Ridge, which turned out to be a region of negative magnetic phenomena. On the other hand, seismic indicators here are anomalously neutral. Thanks to this region became the first object named a seismic gap. In perspective, this could well be the calm before a severe storm. A gap is considered a sign of stress accumulation in the Earth's crust, which, over time, will rupture with powerful earthquakes and even tsunamis. All of this sounds extremely threatening, but who said that there cannot be something truly amazing and beautiful in such a scary place? Biologists are harvesting a rich crop of new species that live and survive in the trench area. In early 2017, all major media outlets reported the discovery of about 500 living creatures in the Kuril-Kamchatka Trench, not just new, but previously unknown to science. Scientists promised to classify and provide more details on this finding, but strangely, we could not find any further news on this topic in the following 4 years. Apparently, classifying these new species is proving to be difficult. If anyone knows more, please share a source in the comments, and we'll give a heart to such a comment. Research on the Kuril-Kamchatka Trench began in the mid-20th century, and it was discovered then that the density of the world's ocean is greatly exaggerated by scientists and enthusiasts who sincerely believed that the volume of biomass in the coastal areas of the North Atlantic is preserved throughout the rest of the world's oceans, meaning its resources could feed humanity for many years. Soviet scientists studied the trench aboard the Vityaz, and since then, no thorough research has been conducted. Furthermore, many of the results of these studies were encrypted. Therefore, as is customary in such cases, if something is not studied, it is assumed that something is wrong there. Rumors started spreading that there is a secret alien base at the bottom of the Kuril-Kamchatka Trench, and there were even claims that their internal organs were found there. However, it was not this myth that recently caused a sensation. A new species of leech, the Johansson's extreme leech, discovered in 2019, caused quite a stir. Of course, it is difficult to expect any positive associations with leeches, but this particular specimen is not dangerous to humans. Its carriers are fish, in this case, the black macrurus. The special feature of this species is its size. The size of these organisms usually does not exceed 25 millimeters in length, but on Sony, it reaches a whopping 58 millimeters, an absolute record, but not the last. This leech-like fish couple lives at an incredible depth of almost 9 kilometers, which is also considered an absolute record. And now imagine how much more amazing things are there. I don't know if there is an alien base or if Davy Jones is hiding his kraken there, but I know one thing, this trench holds many mysteries. Solving these mysteries can help prevent terrible natural disasters and tell us a lot about our planet. We just need to focus on research and science. The first expedition to the bottom of the trench is planned in the near future, and it will involve an exploration apparatus with the symbolic name Vityaz, just like the one that began exploring the Kuril-Kamchatka Trench. Imagine that humanity, having decided to explore a very distant exoplanet, sent a reconnaissance probe to it. It discovers a certain substance that has no analogs known to our science. How can we verify its reaction to chemical exposure? What if it is a local organism that will die from chemical exposure, or on the contrary, will become stronger and start to rampage, as we have seen in movies where not only non-living matter but also living beings behave this way? Certainly, modern science has over 100 terms for defining the concept of life, which is too much, I agree. This means that researchers are still not entirely sure what life itself represents. Often, proteins and cellular structures are mentioned in interpretations, but alien life and their form may not have them. This is supported by the fact that at the beginning of life on our own planet, there were no protein or cellular structures. But we will return to this later. If we take all of the existing definitions and find a commonality, it would be that living organisms are capable of exchanging substances with their environment, grow, respond to external stimuli, and reproduce. In general, the exchange of substances is a property of almost all chemical processes. For example, a burning fire takes in oxygen from the environment and gives off carbon dioxide in return, but it is still considered living. As for reproduction, even computer viruses are programmed for this process. And in terms of growth, even the flames of a fire waiting for grass to burn can grow, and an ice crystal can accelerate its growth with a decrease in temperature. From this, we can see that exchange of substances, growth, reproduction, and response to stimuli are not the only indicators of life. Let's add one more criterion. A living organism creates more complex substances during the exchange of substances. It seems like the solution is found. All living proteins, millions of which make up the basis of life, have just over 20 amino acids. However, even the flames of a fire can break our concept, creating sufficiently complex substances such as colorless crystals like anthracene and phenanthrene. Nevertheless, there are significant differences between substances created by fire. They are not only unnecessary, but even harmful. For example, soot extinguishes fire. On the other hand, substances synthesized by a living organism serve as tools for improving its structure, helping in synthesis and resistance to the aggressive external environment. Moreover, the synthesized substances will be passed on to new generations, which is known as the accumulation and transmission of information. Currently, this condition is considered the fundamental property of life. The ability to accumulate information, whether it's the synthesis of substances useful for adaptation, the transmission of antibodies, or a verb that thickens the hearts of people, it is no longer so important. So, what does it mean that non-living things can become alive? To answer this question, we first need to understand how life originated. There is no single opinion on this matter, but there are plenty of assumptions. For example, an asteroid could have brought life to our world, or it could have been an experiment of a highly advanced civilization. However, answers to these assumptions only generate more questions. For instance, if life was brought by an experiment of some civilization, how did it arise in their own world? It is difficult to imagine that all this diversity of life could have arisen on its own by exploring the living organisms around us. But what if, in ancient times, there was only one form of life on Earth? Modern geologists constantly find stromatolites, layered stones formed by ancient colonies of cyanobacteria. The oldest of these stones is over 3.5 billion years old. There are currently no other records of life from that time, which becomes an argument in favor of the fact that only cyanobacteria inhabited the Earth at that time. However, we should not underestimate them, as bacteria are already complex organisms in which the synthesis of various proteins occurs. Genetic information is stored in DNA and RNA, which function in transmission and transportation. What are the chances that these substances arose on their own and combined? Recently, scientists have discovered biochemical reactions that do not require proteins, but only involve ribonucleic acid and ribozymes. Imagine such an organism as a droplet containing nucleic acids. Some molecules contain genetic information, while others synthesize new RNA. In turn, the RNA creates a shell, but how does this organism feed and reproduce with the necessary molecules? The organism takes them in by forming bonds with existing long chains of RNA through the formation of pairs. It requires a lot of time to form bonds in a new chain, or it is necessary to temporarily raise the temperature. There is also a third way, which involves the help of other RNA. And it's important that a supertask is being performed. A droplet can accumulate and transmit useful data, in other words, it lives. But what makes molecules come together? Now we know that life arises from the connection of non-living elements, and the main thing is the ability to store and transmit information. But there is a phenomenon that plays by the same rules, although it is not considered alive. Of course, we often call it alive, but only in a metaphorical sense. What is meant here? Look at the screen. You can read what is written here, of course, but it doesn't make sense. It's just a collection of letters, and if we say that it's dead, we're right in general. And now, these letters will come together in the right order for comprehension. You already understand what phenomenon works like life, right? It's language, the ordinary spoken, mental, and written language that we sometimes call alive. It accumulates information while alive, and the meaning, an analog of life, arises due to the combination of meaningless, non-living components. Additionally, language can expand by increasing its vocabulary and the number of meanings. These words can also reproduce, forming adverbs, dialects, slang, and narrowly focused vocabulary. Many thinkers, including poets and philosophers, explicitly state that we do not speak language, but rather language speaks through us. This means that we do not control language, rather, humans are the environment and tool for language, and the thoughts that language embeds in our minds are transmitted through spoken or written letters. Imagine how this would work if molecules, for example, rather than humans, serviced language. However, it is we ourselves who use language, as we just discussed. The use of nitrogen bases to form DNA words is what gave rise to life on our planet. Confirms the idea of both philosophers and poets that it is language that created humans, and the emergence of life is impossible without the synthesis and exchange of substances. The cessation of these processes, according to established opinion, leads to the cessation of life itself. However, does this happen in all cases permanently? Let's take a simple frog as an example. It often falls into hibernation right where it lives, and with the onset of winter, the pond or lake freezes, and the frog's heart stops beating, breathing stops, and there is almost no metabolism. But does this mean that life is over? No. It is just on pause, because if you warm up the frog, it will come back to life. There are many forms around us, such as multicellular organisms. It is believed that such organisms can remember and accumulate experience and share it, confirming their individuality. However, what if we disrupt the connections between cells? A simple experiment on the Hydra is striking. The multicellular organism was taught to retract its tentacles in response to a flash of light, but then it was decided to wipe it through gauze. Then, they separated it into individual cells, and after waiting for it to fuse back together, they shone light on it again. The result was astonishing. The revived Hydra remembered what it had been taught and retracted its tentacles when exposed to the light, even when it was a single cell. Planaria do not fuse back together after division, but instead, one planaria can consume the cells of another. They pass on knowledge to each other through ingestion, so by teaching one planaria something and feeding it a piece of another, the knowledge can be transferred. Can humans create life from certain components? Yes, this has been proven by scientists who were able to generate a completely new, never-before-existing bacterium by hiding a DNA chain inside a shell, filling it with RNA and other necessary substances, and then bringing it to life. It was able to eat and reproduce through division, even though it was created artificially. Moreover, a recent group of scientists was able to replace all the nitrogenous bases in DNA, which is equivalent to the number of letters in the alphabet, with completely new ones. Scientists' ideas are going far, and what if new forms of life can live on other planets in various conditions that are unsuitable for us? It is quite possible that we ourselves will become the creators who will bring life to other regions of our universe, but should we sow life on other worlds? This is a separate question for a separate video. If you are interested in this topic, please give this video a thumbs up and write your thoughts in the comments. Earth, like other planets, orbits around the Sun, the most massive object in the system. It takes 365 days, or 1 year, for our planet to complete one full revolution around the star. The path of Earth's movement, or its trajectory, is called an orbit. Today, we know that our planet has the most distant and closest points to the Sun, known as aphelion and perihelion, respectively. We also know that Earth has been on its orbit since its formation many years ago. Many years ago, and many years in the future, our Sun will descend from the main sequence and gradually expand, evolving into a red giant, engulfing all the inner planets of the solar system, including the orbit of Earth. This catastrophe is inevitable and quite interestingly depicted in the story Roaming Earth by Chinese science fiction writer Liu Cixin. According to the plot, humanity decides to build a series of massive engines along the equator of the planet to escape the Sun, which is rapidly increasing in size. Thanks to the thrust of these engines, our planet turns into a giant spaceship, leaving its orbit and moving towards the Alpha Centauri system, which is located at a distance of just over 4 light-years. This poses a risk of destroying Jupiter, and a series of dramatic events unfold, which we will skip since our focus is not on the plot of this story. Instead, let's ask the question: can humanity potentially send the Earth around the Sun and to another system? It should be clarified that the hypothesis of sending Earth to Alpha Centauri is an idea that sounds too improbable to take seriously, and you will understand why further. However, in reality, wandering planets do exist, and they even represent a serious interest for our science. Therefore, let's approach the question of the possibility of moving our planet to an orbit that is 50% farther from the Sun than the current one. Can we increase the Earth's orbit to the orbit of Mars? Let's examine the most basic method that comes to mind. In order to move a celestial body from its orbit, it needs to be deflected by something. Remember in the movie Armageddon where Bruce Willis saved the world by using nuclear warheads to destroy an asteroid on a collision course with Earth? Moving from science fiction to real science, NASA and the European Space Agency plan missions in which they want to use a kinetic impactor to deflect a small asteroid from its orbit. However, unfortunately, such methods would be impractical if the goal was to change the orbit of Earth, with a mass of around 6 sextillion tons, is so massive that any explosive device or kinetic impactor calibrated for such mass would ultimately have one very unpleasant side effect: the destruction of the Earth. Fortunately, there are other methods for achieving the desired goal. For example, the necessary impulse can be divided into a huge number of sequential pushes. This is something that happens today with every launch of a spacecraft, where the rocket and engines provide the necessary boost to launch it beyond the atmosphere. While this is a kind of impact on the Earth, its effect on the orbital motion of the Earth is negligible because the power of even the largest rocket engines is insignificant compared to the mass of the planet. To change the orbit and influence it, we would need 300 billion launches of such rockets. Unfortunately or fortunately, 85% of the Earth's mass would have to be expended on the materials needed to build such a colossal space fleet, leaving behind a withered Earth with only 15% of its current mass on a new orbit, which would be more convenient. Many years ago, and also many years in the future, our Sun will eventually leave the main sequence and gradually expand, evolving into a red giant that will engulf all of the inner planets of our solar system, including Earth's orbit. This catastrophe is essentially inevitable and was the subject of a story by the Chinese science fiction writer Liu Cixin in his novel The Wandering Earth. In his plot, humanity decides to build a series of enormous engines along the equator of our planet to save themselves from the sun, which is rapidly increasing in size. With the thrust of these engines, our planet transforms into a giant spaceship and leaves its orbit, heading towards the Alpha Centauri system, which is located just over 4 light-years away. This action poses a risk of destroying Jupiter and other dramatic events occur, but we will skip over these details because it is not the focus of our discussion. Instead, let's consider the question, is the main idea of the story feasible? Can humanity actually lift Earth out of its orbit around the Sun and send it to another system? One way to accomplish this would be to use ion engines, which create a small continuous thrust and accelerate through an electrostatic system. A similar type of engine was used on a spacecraft whose mission was dedicated to exploring Vesta and Ceres. To push Earth out of its orbit, it would be necessary to build a giant ion engine and place it at a height of 1,000 kilometers so that it does not enter the atmosphere. However, such an engine must be securely connected to the surface of the Earth using superstable beams to transmit the thrust to the planet. The ion engine would need to create a continuous thrust of 40 kilometers per second in the direction of Earth's orbital motion. To expand Earth's orbit to Mars, it would be necessary to convert just 13% of the planet's mass into lunar fuel. This leaves us with a whopping 87% of Earth's mass. The challenge now would be to make the propulsion systems more cost-effective so that we can preserve as much of the Earth's mass as possible. The result would be a withered Earth, left in orbit, but with only 15% of its current mass. But how can we make cheaper propulsion systems to keep the land intact and safe? For example, light has momentum even though it has no mass, so theoretically powerful lasers could be used to create thrust. There is a project called Starshot that is based on this idea, where lasers are installed in certain places on Earth capable of producing a beam to accelerate a solar sail directed towards Proxima Centauri. The necessary power is generated thanks to solar energy, and such a laser system could also be used to create continuous thrust capable of changing the Earth's orbit. However, even with a laser of such power, expanding the Earth's orbit by only 50% would take an eternity of 3 billion years, which is about 8 times the current age of the universe. There is also an alternative method of using radiation pressure to achieve the same orbital change, but in a much shorter time. A much shorter time system consists of a solar sail parked in orbit around the Earth and oriented to deflect solar radiation. According to a 2002 study, photons from the Sun reflected by the sail will move the center of mass of the Earth sail system, altering the orbit of our planet over time. However, we would need a solar sail 19 times the diameter of the Earth, or over 240,000 kilometers wide. On the other hand, this solution would save a lot of time compared to the previous method, which relied on using lasers. With such a large solar sail, only 1 billion years would be needed to move the Earth to the orbit of Mars. Finally, there is another method we can consider, using asteroids and comets to subtract orbital energy from the Earth and increase our planet's orbit to the desired size. The idea is to slightly alter the orbit of a large number of objects in the Kuiper belt so that they pass several thousand kilometers from the Earth's surface. In practice, we are talking about the use of the same system that has been used since the 1970s in several space missions, where the gravity of planets was used to accelerate or sometimes decelerate probes. This effect is mutual. Not only does the spacecraft speed change after the flyby, but the planet's orbital speed also changes. If the flyby accelerates the probe, the planet's orbital speed decreases. The difference in mass between the spacecraft and the planet is so great that the slowing down of the planet's orbital motion is imperceptible. However, if an asteroid flew by instead of a probe, the subtraction of momentum experienced by the planet would be much greater. After a sufficient number of sliding passes of asteroids or comets, the Earth's orbital motion could be slowed down to such an extent as to expand the orbit radius to 1.5 astronomical units, the distance from Mars to the Sun. However, even in this case, calculations show that this option is not feasible, as not only the mass of the object, but also its speed during the flyby must be taken into account. It will be necessary to choose objects with very eccentric orbits about 300 astronomical units long. This means that the Kuiper belt will not pass between two consecutive close passes of the same object for at least 1,000 years. Today, as we see, there is no fast and cheap way to move the Earth to another orbit. The threat posed by a wandering Earth is currently just science fiction, but in the future, it will become a reality. With the evolution of the Sun, in approximately 1 billion years, the Earth will receive 10 to 11% more radiation than it currently does. This will lead to an uncontrollable greenhouse effect that will evaporate the oceans. When that time comes, our descendants, if they still exist, will have to find a solution to the survival problem presented in the book by Lucas. Moving the Earth from its orbit will not be a practical solution, so the only possible salvation could be to terraform and colonize the satellites of our gas giants, where a warmer and more hospitable climate will appear due to the same increase in solar radiation. By the way, the Chinese have already made a film based on this story, fragments of which you have seen in this video. But frankly, the book is much more interesting. Lastly, this is an experimental topic for us. There are still many ideas described in books or shown in movies that we can discuss in these videos, even creating a whole section. But the question is, how much do you find it interesting? Write in the comments or give a thumbs up under this video. The more responses we receive, the faster we'll know if this section is of interest to you. Until our next interesting meeting, every night, astronomers explore the sky in search of possible habitable worlds and radio signals. There have been no signs of alien life detected yet, but are all these searches in vain? The question of whether we are alone is very important, as the answer greatly influences our place in this vast space. There is a hypothesis called the rare Earth hypothesis, which suggests that we should not search for life among other stars. But is this hypothesis true? Let's start with broader concepts, then focus on the hypothesis itself, and then look at recent discoveries to see if they coincide. We propose a plan for this theory, and on our channel, we will discuss many different topics, so it will be particularly interesting going forward. You have probably heard of the habitable zone around stars, where exoplanets are located at a suitable distance for the emergence of life, not too hot, but not too cold. This zone is also known as the Goldilocks zone. But did you know that there is also a habitable zone in our galaxy? Not all galaxies have a habitable zone. The further a star is from the galactic center, the less its metallicity, or the lower the amount of heavier elements than helium. This decrease occurs because heavy elements are created in the hearts of giant stars and supernovae, and such stars are concentrated in much higher concentrations near the galactic center because there is enough material for their formation. This means that stars in the most distant parts of the galaxy may not be able to support life. Typically, a supermassive black hole is located at the center of the galaxy, which can emit a huge amount of X-rays and gamma rays. Any nearby exoplanet will be constantly exposed to this deadly radiation, and life could never thrive in such conditions. Our spiral galaxy has dense arms that extend to its edges, and these arms are also deadly to life. Stars regularly pass near each other and disrupt the orbits of exoplanets. Imagine if Earth suddenly moved into Mercury's orbit. Additionally, there is also the problem of nearby supernovas in these regions, such as the supermassive black hole, which regularly emit deadly radiation. Therefore, the habitable zone of the galaxy is quite close to the galactic center, where there are enough complex elements, but it is located far enough away from the core and the arms to avoid gravitational disturbance and radiation overdose. We are still in the early stages of understanding which part of the galaxy is suitable for life. In the case of the Milky Way, all of these factors would make the vast majority of stars unsuitable for life, and only a remaining portion of stars must be of the appropriate type and have the right planetary structure for life. Previously, we thought that every star had a habitable zone, a theoretical distance at which liquid water is possible. However, this is a very simplified view that does not take into account the spectrum or viability of stars. For example, less massive stars emit much less visible and infrared light than main sequence stars, but they can emit a huge amount of X-rays and gamma rays. This means that their habitable zone may contain water, but the levels of X-ray and gamma radiation may be so high that complex molecules can be torn apart, killing any prospects for life. The variability of our sun's luminosity is less than 0.1%, but for other stars, it can vary up to 500%. Therefore, the boundaries of the habitable zone shift as stars become dimmer and brighter, meaning that habitability measures will fluctuate in and out of the zone, killing any chances of life. Even if we discover a star of the right type, it is far from certain that a planet there will be suitable for life. We also need the right planetary setup. In our system, rocky planets are close to the star, and gas giants are rarer, but in other stellar systems, the vast majority have either only rocky worlds or hot Jupiters, gas giants close to the star. However, in our unique setup, life was able to emerge, and there is a direct correlation between the number of planets in a star system. There is a direct correlation between the number of planets in a star system and their circular orbits. Systems with only one or two exoplanets usually have wildly elliptical orbits, meaning that the exoplanet may enter and leave the habitable zone throughout the year, destroying any potential life. However, systems with more planets and larger exoplanets have orbital resonance, which creates much more circular and stable orbits. This allows the exoplanet to remain within the habitable zone throughout the year. Orbital resonance is too complex to explain fully, but its essence is that such a system is in balance and holds each planet where it should be. Even if Earth were to fall too close to the Sun, orbital resonance would elongate its orbit and pull it back. However, even if we obtain orbital resonance, the chances of finding life on rocky inner worlds and outer gas giant exoplanets are small. Models of the early solar system show that Jupiter played a crucial role in the emergence and development of life on our planet. Jupiter has orbital resonance with every asteroid in the asteroid belt, holding them together and between itself and Mars. Without this influence, Earth would be constantly bombarded by asteroids and life could not thrive. In fact, if it weren't for Jupiter, life may not have begun at all in the early days of the solar system. Jupiter was actually drifting into the inner part of the solar system, threatening to destroy the inner planets, but it has a unique resonance with Saturn, and Saturn with Uranus. This resonance meant that Saturn pulled Jupiter out of the inner spiral, preventing collisions with Earth and Mars. Therefore, in order for life to emerge on an exoplanet, in addition to other things, a unique planetary setup is needed. However, even this is not enough to become habitable. The right type of planet and satellites are also required. First of all, the size of the planet requires the correct gravity, otherwise it can be very inhospitable. If the atmosphere is too bright, liquid water can simply evaporate into space, as happened with Mars. The planet's atmosphere must also be suitable in composition, otherwise it will be unsuitable for life, like Venus, whose atmosphere has a high level of carbon dioxide, making it the hottest planet in the solar system, despite being in the habitable zone. Plate tectonics, biological effects that create mountains, volcanoes, earthquakes, and deep-sea trenches, are all crucial to life. First, we believe that life should begin around hydrothermal vents caused by tectonics, so it cannot exist without them. Second, tectonics is extremely important for complex life, but more on that later. Tectonics is created by the mixing of molten rocks in the core of the Earth. This iron-rich magma rises to the surface, participating in the creation of the Earth's magnetic field, which further protects it. Without a magnetic field, as you know, Earth would quickly become uninhabitable. Plate tectonics helps with radioactive decay in the planet's core, internal heat, and, surprisingly, our moon. Our moon is not ordinary, it is undoubtedly the largest moon in comparison to the size and mass of its planet, constituting 27% of Earth's mass. This means that its gravitational attraction on Earth is enormous, creating tides, heating the planet's mantle through friction, and without the massive moon, we may not have plate tectonics. But the moon does something else, it stabilizes Earth's axial tilt. As we know, Earth rotates under a slight tilt, which results in seasonal variations. Well, the moon's tidal forces keep this tilt constant and stable. See how many nuances there are. Let's say we found an exoplanet in the habitable zone of the galaxy, around a star of the correct type with the correct planetary structure, the right size, composition, and plate tectonics, but without a moon. Would there be life there? Quite likely, yes. Scientists are currently exploring Mars to find out if there was life there a billion years ago when there were oceans, plate tectonics, and a dense atmosphere. If evidence is found, then those distant worlds almost certainly have life. But it is important to understand that it is not a complex form of life, but rather more similar to bacteria. Complex life, such as multicellular life or intelligent life, requires special circumstances to arise. In fact, life existed on Earth for at least 3.5 billion years, but it was only 540 million years ago that truly complex, multicellular life first appeared. Over the course of 3 billion years, the Earth was populated only by simple organisms, gradually developing much more complex structures. However, even at this stage, animals and plants were still far off. These early multicellular organisms resembled sponges and were composed only of clumps of cells. But you know what's amazing? The cooperation between cells seems like pure chance, as the likelihood of it happening again is extremely small. It took about 800 million years for the probability of multicellular life to increase significantly. But even this is not complex life. A natural revolution was needed to create our complex ecosystems, which occurred approximately 541 million years ago as a result of an event called the Cambrian explosion. Imagine that the Ice Age has just ended, and the Earth is gradually heating up. Glaciers are melting off mountains, releasing a huge amount of nutrients into the ocean, and there is a total bloom of algae. The atmosphere is filled with oxygen. These nutrient-rich mountain ranges existed only because of tectonics. So the Cambrian explosion could not have happened without it. Therefore, tectonics seems vital for complex life. Abundant nutrients and oxygen meant that organisms could afford to burn energy and move to other places to eat. Then, some evolved to hunt other species. Over millions of years, life progressed from simple sponges and seaweed-like creatures to arthropods, cephalopods, vertebrates, and sea stars. Throughout all this time, we're talking about life, but let's face it, we can hardly call these Cambrian creatures intelligent. So, to sum up, what does a planet need for life to exist? The planet must be in the habitable zone of the galaxy, orbit a star of the right type, have the right type of orbit, have the right type of planetary neighbors, have the right size, have the right composition, have tectonics, have a large moon, and a natural cataclysm must occur that leads to multicellular life. That's how many factors there are. Earth is incredibly unique, and the likelihood of finding its twin is vanishingly small. But maybe we've been looking at things the wrong way in recent years. This hypothesis has been challenged by unexpected discoveries from several moons of Jupiter and Saturn, which have liquid water beneath the surface and likely hydrothermal vents, which could hide life. This has led some scientists to doubt the unique Earth hypothesis. If we discover life, no matter how simple, on such remote oceanic moons, we'll have to discard this hypothesis because we'll have a new model of planetary habitability, or rather, satellite habitability. Furthermore, there are many Jupiter-like planets in the galaxy, and since both of our gas giants, Jupiter and Saturn, have oceanic moons, Enceladus and Europa first and foremost, we can assume that there are many exomoons that are perfectly suitable for life. We may never find an Earth twin, but it seems there's a good chance that somewhere in space, we'll discover a world with even more intricate life than our own.